Hello, my name is Christina, and today I'm going to be covering the topics discussed in detail in Module 1 for Psych 642. There are 5 general topics that were presented in Module 1, first being distributions, which is how a set of data is spread out, measures of central tendency, which refers to the center of a distribution and its values, mean, median, mode, measures of dispersion, which is the data set distribution around measures of central tendency, and speaking about range, variance, and standard deviation. Also, data integrity, which in general is the accuracy, consistency, and trustworthiness of data. And data transformations, which is the conversion or modification of data for analysis or modeling. And really, my general intention with this presentation is to show how all these topics are integrated together. Before I move forward, I just want to present a couple additional texts that were analyzed in this module, one with being level of measurement by Borgata and Bornstedt, as well as things I've learned so far by Jacob Cohen. Scales of measurement is an important topic to understand this module, as ordinal, nominal, interval, and ratio scales are best understood in the topics and measurements used throughout this module. The 1980 Borgata article describes that scales chosen are directly related to the statistical measure or any mathematical operation used with that scale, and that data transformations of the scales are to leave the uh, variables undistorted. And Cohen speaks much on the power and effect size, and Cohen's D is the measure of statistical power, and that's a unifying concept in all statistical processes. And he really makes a great point on the need to plan for research and plan statistics before and in post hoc analysis. And that really goes to the integrity of the data itself and research itself. And cherry picking really what statistical measures are used is calls into question the integrity of data. So moving forward on to the first topic, distributions, what they are, what they mean, and why it's important. Distributions show how data spread out, and the distribution of data provides information on statistical patterns. So characteristics and tendencies of the data set is important to know how the data is distributed, as predictions and conclusions about the data cannot often be made until the distribution is observed and understood. Many natural phenomena can be observed in a normal distribution, and many statistical analyses require normally distributed data. So it really shows how the data is spread out, as you can see. And there are some characteristics of distributions, first being shape, center, and spread. So the shape, a bell shape would be a normal distribution. It can be symmetric, skewed, or uniform. And this really shows the cohesiveness of all the topics already discussed. So measures of central tendency and the measures of dispersion are characteristics of distributions. So in reference to normal distributions also, um, this is why, as we get into later, often data is transformed to meet the population norm from a sample. And that's not to say that non-parametric statistics cannot be used, such as the chi-square test of independence. These are just some visual representations of distributions, and there are many different distributions. This is a histogram that was completed in the lab in this module that looked at depression scores and friendship interactions. Histograms are one way of looking at distributions. In this, you can see that it is skewed and would need to be transformed in order to be observed as a normal distribution. Other visual representations of distributions are box plots, strip plots, kernel density plots, and violin plots, all of which help in different ways to observe the distribution of data. As you can see in the box plots, oftentimes uh, that is preferentially used for interquartile range. Moving on to measures of central tendency, mean, median, and mode is depicted in the Schreiner article. Do you see what I mean? Indices of central tendency. We learn different scales of data, nominal, ordinal, interval, or ratio have preferred methods of central tendency that depict the data better than others. For instance, mode in nominal data would provide the most frequent data present in the nominal data set. However, mode can be unstable and not the greatest representation of central tendency unless one category is truly dominant. So the mean is equivalent to the sum of values in the data set divided by the number of values. The median is the middle value in the data set, and the mode is the value that is most frequently occurring in the data set. Each has its own strengths and weaknesses, making it suitable for different types of data analysis. The median and mode are less affected by outliers than mean, making them more suitable for skewed or heavily tailed distributions. Additionally, in focusing on the mean, there are different types of means: arithmetic, harmonic, geometric, and trimmed means. And speaking of robust estimators of the mean, this can trim data in the most extreme cases to normalize the data and prevent extreme skews in the data set. The outliers shown to the left in the box in the plot show points outside the normal range, and removing 5 to 10% of extreme data points is often done in trimming data to calculate the means. As stated by Jacob Cohen, graphical depictions of data are especially important in bivariate data as scatterplot shows individual data points. Moving forward to measures of dispersion, we'll discuss variability, standard deviation, range, and more. Measures of dispersion are important for assessing consistency or variability of data. They provide information on how values in the data set differ from central tendency. Some measures of dispersion are range and interquartile range, variance and standard deviation, as well as coefficient of variation and mean absolute deviation. The range and interquartile range are a measure of dispersion. The range is the simplest measure of dispersion and is calculated as the difference between the maximum and minimum values in a data set. The interquartile range is a measure of statistical dispersion or spread. The interquartile range provides dispersion of the middle 50% of values in the data set. In discussing variability and standard deviation, the variance depicts how far the values of the data set are from the mean value. It is calculated with the average of square differences from the mean. The formula depicted shows the population variance and the sample variance, where X represents each value in the data set, and mu or X bar represents the mean, and N is the number of values. In reference to variance, the homogeneity of variance means that variance is similar across different groups. The standard deviation is the square root of the variance and provides a measure of the amount of variation or dispersion of a set of values. Moving on to data integrity. Broadly speaking about data integrity, it is the consistency and accuracy of data. I wanted to take a moment to focus on data integrity, but also the representation of data itself. Statistics can quickly become a pick and choose method of representing data between different options of central tendency to transformations of data itself into normal distributions. The integrity of data itself can be called into question, but also the way it is represented. Statistics is a tool that is used to calculate and model data, and it can be used for and against the data. Choosing accurate representations and calculation of data is imperative in the sciences. the text How to Lie with Statistics, it shows how data can be represented and ways to maintain the integrity of data. Some points are being skeptical about the correlations, always looking at the axes on a chart, ensuring that the descriptive statistics are observed, as sometimes there's missing numbers and that can be done intentionally. Observing if there's bias in the sample selection, and understanding that a sample size can misrepresent the constructs that are being measured. Lastly, there are some inferences in post hoc analysis that can be made that can question the integrity of data as well. As you can see in that representation, it's the same data but different axis, and you can see the distribution also and how that's affected. In this section, I also wanted to discuss statistical power. It's a unifying construct as discussed before, and is the probability that you will reject the null given that it is false. And this is really getting into hypothesis testing as well. Statistical power is a function of sample size, effect size, and alpha. It's the distance between observed means in terms of standard deviation units. So it's getting into central tendency and dispersion as well. Cohen's d is a z-score, but it is the score of change. Moving on to data transformation. This includes log transformation, square root transformation, z-score transformation, among others. Data transformation is the adjusting, converting, or re-expressing of the data to allow for suitable statistical analysis. Transforming data can help assumptions of statistical methods, such as assumption of normality in parametric statistics, and improve the interpretability of results, allowing for the data to be more amenable to analysis. Log transformations involves taking the logarithm of each data point. They're used to stabilize the variance in the data. It provides symmetrical data and helps show linear relationship between variables. That's a common basis for log transformations are natural log and base 10 log. They're useful and for data that exhibit exponential growth or decay. Z-score transformations is a standardization that involves transforming the data to a mean of 0 and a standard deviation of 1. It's achieved by subtracting the mean and dividing by the standard deviation for each data point. Standardization of data using z-scores allows for direct comparison of different variables and facilitates the interpretation of the relative position of individual data points within a distribution. Though normality is often referenced in data transformations, there is an importance of variance in data transformations before applying statistical techniques. It's important to ensure the variance of the data is approximately constant across different groups or conditions. This refers to the homogeneity of variance. Transformations stabilize the variance to meet assumptions of statistical methods such as ANOVA or linear regression. Skewed distributions or non-constant variance violates many statistical assumptions, and log transforms and square root transforms can help make variance consistent and the data symmetric. Normalized data can help hypothesis testing to be more reliable, and the results are easier to interpret. And with this, another point is that outliers inflate the variance, and transformations can help with that. The relationship between variables is more accurately compared and assessed with the transformation of a variance. In conclusion, I just wanted to show some relationship between topics. It's evident in each topic that's discussed that there's a relationship between each one, and then also there's going to be a relationship with each one moving forward. And this is just a visual depiction of that. And it's going to be important to understand these topics moving forward as they do contribute to inferential statistics, hypothesis testing, and other topics that will be discussed later on. So this concludes my presentation on Module 1. I hope that it showed at least visually the topics that were discussed in this module. Thanks so much.